So I'll just go over what we did in the last session. So in the last session we started out with uh, all the three types of inference: maximum likelihood, MAP, and Bayesian inference, and saw the difference between the three. So again, just a quick refresher. This first term, this first term is the only one being considered in MLE estimate. The entire numerator is being considered in MAP estimate, and all the three terms are considered in Bayesian inference, the full Bayesian inference. Then we saw a few examples of assuming independent, like all the data is IID, how we would go about calculating the likelihood. And so likelihood would just be the probability of each data sample given your parameters of the distribution. And then we saw how MLE estimate is the same as cross entropy estimate, which is the same as getting the distribution that is the minimum KL divergence. So we saw the formula of entropy, cross entropy, a bit of information theory. From cross entropy, we proved how minimizing cross entropy is same as minimizing KL divergence. And then and then we got this cross entropy loss function. Then we saw how maximum likelihood estimate is the same as cross entropy and proved the equivalence between all the three properties. And then uh, I told you kind of like something that you could have tried by yourself is get the maximum likelihood for given your data samples, get the maximum likelihood estimate of uh, which parameters would be the best if you try to fit a normal distribution so that you can get a maximum likelihood. Then if you would have just differentiated it and tried to prove it yourself, you would have come up with this mean and variance that are like exactly the mean and variance of your data samples. Then we went over to MAP estimate, and then uh, in MAP estimate, we said we would consider the prior term as well, and how in order to do the maths a bit easier and also intuitively that don't need to change the distribution of your parameters. Uh, you would ideally want a likelihood distribution that is conjugate to your prior, in the sense when you multiply this term with this term. So p theta is your distribution on prior, and this p theta is the same distribution given new data. So you would want that the distribution still remains the same. And if this is the case, we call these as a conjugate pairs, where if the theta belongs to a distribution B, then a family of distribution B, say normal, then multiplying it with this new distribution A, you would still get a distribution with some other parameters, but that distribution should still belong to the family B. Uh, and then invariably we saw how maximum likelihood is same as MAP with a uniform prior over your parameters. And then this was an example of how I think then some people had doubts in this section where how you would try to define your parameters. So for prior distribution, the likelihood is some p of x given theta. So here the random variable is always x. Your data basic random variable that represents your data, and then when you multiply it with your prior, in this the random variable is your parameter uh, for this distribution. So if it was normal, then this was x and say mean mu and some variance. So in this distribution, you would either have a distribution on your mean or variance. So Yep. And then if you multiply these two, then you would have a new mean, uh, updated theta, theta hat, theta dash say. Then you would still want that if your prior distribution on new belong to some family A, then this updated theta should also belong to this family A, this updated distribution on theta. So we saw how normal is a conjugate prior to normal itself over the parameter nu. So if you take this normal, and here if your distribution A is again another normal distribution over your mean nu, then the updated distribution that you get is still a normal. So yeah, so this was our example where you can see this is the likelihood, the bottom one, and it's defined over this random variable x, and the parameter that we are interested in is the mean, which is here theta. And then this the prior distribution theta is also normal, which has some new other parameters, mean and sigma square. And and whenever you need to see which of the distributions conjugate to other, you always need to see that the functional form that you get after multiplying these two is the same as the functional form of your prior distribution. And we saw that so normal a simple way to summarize the normal distribution is a functional form wherever you have a quadratic wherever you have a quadratic term in your exponent. So that generally is basically how you would summarize a functional form of a normal distribution. And then we saw if you multiply these two together, then you would just add up. Uh, yeah, so a quadratic plus quadratic is basically still a quadratic, and you can rearrange the terms and see for yourself that this one would be a quadratic in theta, and since it's a quadratic in theta, we can say that it's still a normal distribution over theta. Uh, and yeah, and an interesting thing is if you would do this, and then the updated mean that you would observe would be kind of so you started out with mean uh, you started out with mean nu over theta, and then you saw some of the samples x's, and then the updated mean you would end up would be nu plus summation of x's. So initially you had some prior distribution over you had some prior knowledge about your mean, and then you saw new data points, then you are now trying to shift your mean towards those data points. So you can try this by yourself. Just multiply these two and see in this functional form how like what's the um, how should I say? So compare this with theta minus the whole square divided by. So compare this with this, and then you would get this expectation over your theta, and that would be like this. And then the other example of conjugate distribution that we saw was gamma distribution is conjugate to normal. But now here whenever you say two distributions are conjugate to each other, you all and if the prior distribution has multiple parameters, you need to define over which parameter it's conjugate on. Like you are defined in for previous example, we defined a prior on the mean, and now in the second case we are defining a prior on the precision, and precision is nothing but 1 by variance. So uh, if you define your prior over the precision as gamma distribution, and then you multiply both of these again, then you would uh, also get a gamma distribution. Yeah, uh, and again over precision. So again, this is something you can try this at home. just multiply these two together, the gamma distribution over your precision and normal distribution. And then we started with an example, but we left off in the midway. So I think, yeah, I would again revisit this example. So any doubts in the previous lecture? So Deb had one on the Discord channel, and yeah, I would address it while going through the examples. But apart from that, any other doubts? Okay, so I'm assuming not. So yeah, just in case if anyone is not familiar with beta distribution, okay, yeah, I'll just ask. Uh, does anyone want me to go through beta distribution, or you are just familiar and I should just skip ahead? A thumbs up or anything would be nice.
Hi, I mean, I understand beta distribution, but I don't know if you want to go through the derivation or you just want to want to use beta distribution as an example.
So yeah, the derivation between the if you mean the derivation of how uh, beta the relationship between beta and gamma, so that's a bit complicated, and I would love that if you would just go through it by yourself, but I think that would take up more time and it would be another direction. So not the derivation but general familiarity with beta distribution.
Yeah, so I mean, what I understand, beta is like a probability distribution. So its support is between 0 and 1. So it's a probability of probabilities. And it's got like parameters as alpha and beta. And I think the expectation is something like alpha plus beta divided by 2 or something. I don't remember the expectation, but it's something like that.
Yeah, so that's fine, but what about, like, since there are just three people here, so I would just, yeah, Kushal, Aryan, I would just leave Paul if that's fine.
Yeah, even I know the basics, like what a beta is. And if you can just go through it in a minute with graphs or something, it would be good also.
Okay, yeah, fine. So uh, beta, the word beta comes from this beta function. So yeah, beta function is just a name. So this function basically represents the integral from 0 to 1 x raised to m minus 1 minus x raised to m minus 1 times dx. So the value of this integral is, yeah, whenever I say beta of 3, 4, just plug m is equals to 3 and n is equals to 4, and the value of the integral that pops out is just your beta distribution. Not beta distribution. The value of beta function at those particular points. So it has some properties, like you can see that it's symmetric between m and n. So beta of mn is equals to beta of nm, and yeah, of course, from the limits of integral, you can see the x would only go from 0 to 1, and you can also replace x with sine square theta. Then you would have and yep, and then just a similar form, but now instead of x, you would have sine theta and cos theta, and so it just helps you to evaluate your function at some point. And then there is also this gamma function, which is e raised to minus x. So the beta distribution and gamma distribution both comes from these functions. So that's why they are named like that. And here x ranges from 0 to infinity. And this is the you can prove that beta of mn is equals to gamma of n, gamma of n, gamma of n plus n. And I won't go through the proof of this, but this is like whenever people talk about beta and gamma, they generally uh, convert it into this and then evaluate beta function, because the evaluation of gamma function for integers is pretty easy, and because it's also called um, not approximation but a continuous function of the factorial, because if n is an integer, then this is just n minus 1 factorial. So it becomes easy to evaluate your beta function and gamma function. Yeah. And then also gamma function also has some nice properties, like yeah, from this only you can prove this, that uh, so yeah, so uh, and mm, okay, so this is all about beta and gamma function that I want to talk about. Then, and from this we just get a beta distribution and gamma distribution itself. So a beta distribution, let's say I'll just represent so this is PDF of x, and we are assuming x comes from beta. Then what you would want is c of x raised to, this is the functional form of beta, beta of a comma b. So, and then you would always want this to integrate it to 1. So uh, that's why I just put a constant here, and if you want this, then you need this should be equal to 1, and c is just a constant, you can take it out, and this is nothing but your beta function. So c times beta of ab is equals to 1, and c is equals to 1 by beta of ab, which is nothing but a plus b. So this is how your beta distribution looks like. And in terms of graph, it's quite uh, it gives you many forms to deal with. So let's say if x was equal if I have a is equals to 1 and b is equals to 1, then the beta simply becomes a constant. You can see that, right? PDF of x is simply c of x, a is 1 and b is also 1, so the powers become 0 and it's just a constant, which is yeah. Then if if a was say 2 and b was 1, then this would become a linear function, because PDF of x, this is a constant, PDF of x would be yeah, a was 2, then x raised to 1, and 1 minus x raised to 0, then this would be just c of x. And so if you vary a and b, then you get many different types of graph, and that's why it's kind of one of the famous functions that it's generally like uh, varying x or varying a or b. So either you would have this form of peak or this peak, and varying a or b would take this peak to the right as much as possible or to the left as much as possible, and same with inverted as well. So if a is half a is half and b is half, you would get this form of distribution where uh, it's c of a minus half minus 1 is just minus half. So c of x raised to minus half and 1 minus x raised to again minus half. So it would be like c of under root of x minus x. So yeah, the graph of this is something like this, and the more you shift B or A, it would just get skewed further. And similarly, if we have A is 2 and B is 2, then this would be C of x1 minus x. Okay. So you can see it's just a quadratic function. So this is how beta distribution looks like. But the main thing I would just like hope that you go through the proof of this. It's quite detailed, and but yeah, it's nice. So whenever just people talk about beta function and they need to evaluate, they don't directly just go and evaluate this integral, but they convert it to this, because evaluating gamma is sometimes more easier than evaluating beta. As I said, if I just give you mn and s integers, you can just plug in the factorials and you can evaluate your beta. Okay. So and back to our example earlier. So the statement that I wanted to make last time was beta is conjugate prior to binomial. So let's say my probability of x given theta is comes from a binomial distribution of x, and okay. Uh, what are the parameters of a binomial distribution? Yeah, I guess I asked this earlier. So let's say it's just n comma p. N are the number of trials, and p is just the probability. And now if my theta, and when I mean theta here, the I don't want to see this as p because it would get confusing with, okay, let's just say it's theta, probability of success. Yeah, so I'm defining my prior over this variable theta, and I want it to be a gamma function. Oh, sorry, beta function. Let's just a comma b. And then I'm saying this and these two are conjugate to each other. So let's just evaluate what this comes out to be. So since it's binomial, it's ck. Just at a constant of x raised to k, 1 minus x n minus k. Like evaluating this on k, and then for beta, okay, no, so this won't be x, this would be theta. Oops. Okay. Yeah. So so this is my binomial distribution, and my beta says again, this is beta. Again, some constant c dash, theta of theta of a minus 1, 1 minus theta of b minus 1. So yeah, and then if I just multiply them, then I get a new constant c double head, say this becomes theta k plus a minus 1 and 1 minus theta n minus k plus b minus 1. And then you can see that this is again just a beta distribution with parameters k plus a minus 1 and n minus k plus b minus 1. So any doubt in this proof? And I would force you to kind of go through these over all the conjugate priors. Like in last lecture we went through the the conjugate prior of normal as normal over mean, but yeah, go through normal with gamma over precision, this, and then you can find some examples in the course itself of other conjugate prior distribution. and try to prove all of these by yourself. So, but yeah, any doubt in the statement, any doubt in this proof? Okay. Uh, so the example in the last lecture that we were covering and we kind of left off was the same one. Let's say that um, okay, yeah. So mm, yep, the example we were dealing with is, let's say we just only have the information that Arsenal is playing a league and it won 30 matches out of 38. And we want to model the distribution of Arsenal success, and we try to model it via binomial distribution. Um, yep, let's say theta is the success probability, same as above. And we saw if we did just the likelihood derivation, because we don't have any information over this success probability theta, we just want to do yeah, a simple likelihood derivation of, okay, given this data, how likely my this data is over my parameter theta, then and then it would be nck theta of 30 38 c30 theta of 30 and 1 minus theta of 8. uh, and if you see, this is just the likelihood, like pi of over all your data samples, probability of probability of success, seeing that data sample over your given your parameters theta. And for binomial distribution, this just evaluates to theta if it's a success and evaluates to 1 minus theta if it's a failure, and we have 1 minus theta failures and theta successes. And then we saw that if we just derive this over theta and equate it to 0, we would get theta is equal to 30 by 38. Which is not surprising, right? Like if I give you this data and say what's the probability, uh, if it comes from a binomial distribution, the best value that should fit to it should be 30, that the probability of success is 30 by 38. And so it's like if you are tossing a coin and I say you saw you saw 7 heads and 3 tails, the likelihood that the coin is biased is a bit more. And so you would the best probability that would estimate the bias in coin would be like the head probability of it's 7 by 10. But that's not always the case, right? Because these 10 you also have this prior knowledge about your coin, that you had you had done 100 trials previously over the same coin, and during that time it landed kind of equally in both heads and tails, and you would also want to incorporate it here. So continuing this example, as in this tournament, Arsenal won 30 out of 38, but it had played in the past as well, we uh, and we would also want to incorporate that information. So let's say in the past tournaments, Arsenal played 100 matches and won 65 of them. Then the thing we are doing simply here is evaluating. Yeah, and now we would just assume conjugate prior of, as I said, beta distribution over your theta, and we would essentially be doing the same thing, but yeah, just n would be 38 and k would be 30. And what you would see is you will again get this new form. So okay, I'll do it again. Okay. So how would you, and then you need to differentiate this part. So let's say let's say this prior distribution comes again with parameter a comma b. So your prior would be this is your prior. And your likelihood would be so your updated theta. This is your posterior. Map estimate would be just the product of these two, and ck theta a minus 1 minus theta b minus 1 times theta k. So we are essentially doing the same thing, just we have the c and c hat constants over here, and we saw this is a new constant, let's say, and then theta k plus a minus 1 and 1 minus theta n minus k plus b minus. And now what we want to do is uh, we just want to see the optimal value of theta that would maximize our estimate. So we would just differentiate it with respect to 0, no, with respect to theta and equate it to 0. So this would be again similar to what we did. So there is this constant out and this is 0. So the constant will just cancel out with, yeah. So I'm just ignoring this constant for now. So this would be k plus a minus 1 theta of k plus a minus 2 and minus theta and minus k plus b minus 1. And then plus theta k plus a minus 1 and minus k plus b minus 1 times 1 minus theta and minus k plus b minus 2. And then we are differentiating it with respect to theta, and here there is a minus sign, so this would be minus. So like minus 1, I just took it out. And then this is equal to 0, then I would just either say, just taking this entire thing here, we have this. Yep, I just took the negative side and took it to the right hand side, and the right hand side was 0, so we have a positive term here. And then since we are equating this to 0, so my battery is a bit low. Give me a moment. Isn't the record? Yeah, so we are just equating this to 0, and then I can just divide both the sides. So, yeah, this was our original equation. I can just divide both the sides by n minus k plus b minus 2. So this entire term would go away. And here we would just have 1 minus theta. So all I did is just divide by n minus k plus b minus 2. And similarly, we can divide both of these sides by theta of k plus a minus 1. This would go away. Yeah, we have just theta. Oops, sorry. we would divide both of these sets by theta of k plus a minus 2, since this is the bigger term here. Here we would be left with just theta and this entire term. So I kind of modified in the same equation, but I think you can see what we just did, right? So yeah, I just we took the negative sign and shift over to 0, and the negative sign went away, and there is this equal to sign, and then we divided both of these sides by 1 minus theta of ratio n minus k plus b minus 2, and this entire term went away. Okay, this should be on. Yep. So this is the final equation that we have, which is now simply k plus a minus 1 or n minus k plus b minus 1, which is theta of 1 theta divided by 1 minus theta. I think it's called component dividendo, and you can just apply your component dividendo to this, and what you would come up with theta is k plus a minus 1. Okay, it's this is numerator and this is denominator. So all I'm doing is numerator minus denominator, numerator plus. So this would numerator plus denominator would just leave me with 1, and numerator minus denominator would leave me with you can just evaluate it directly rather, and all I want to say is the theta that you get is k plus a minus 1 and n plus b plus a minus 2. So initially the theta that we got was this is nothing but k by n. K is the number of wins and n is theta, and now we have this prior distribution with parameters a comma b, and this is how you changed it. But so okay, I'll just call this is a test. And now I'll also do a full Bayesian inference estimate, and here probably your deb or doubt might get clear.
I'm confused. How did you get the theta, this value?
Oh, yeah. So from this equation to this, you are saying?
Yeah.
Yeah. That's you get like equated. Yeah. So if you are familiar with component dividend, so what it is contains numerator and numerator plus denominator.
You keep breaking off. I don't know if that's for everyone. I don't know if that's for everyone.
Yeah. There's some audio. There's some audio.
Yeah, so you can see by equation and you can get if you perform this, then you can also perform it on the LHS and RHS, and the equality would still hold. So, so, yeah, if you aren't familiar with this, you can just like take all of these towards your left and you just evaluate rather directly, which is 1 minus theta k plus a minus 1 is equals to theta of n minus k plus b minus 1, and then this is k plus a minus 1, multiplying it with 1, this becomes theta of n minus k plus b minus 1, and I'm just taking this theta over to the right hand side, and then it would become plus k plus a minus 1. So all I did was multiply this to this, and I got this, and multiply this to this, and took it to the right hand side. The theta term is a constant. And, yeah, both of these terms gets added, and then this becomes theta of minus k and plus k gets cancelled, n plus a plus b minus 2, k plus a minus. So the theta you get is n plus a plus b minus 2. Oops, no. K plus a minus 1 divided by n plus a minus. And it's just like take the numerator, and if you do this over the right hand side, you can also do this on the left hand side. So you can directly get this from that. So this is your new estimate of your theta based. And here, if I'm just taking an example, then we know it 130 out of 38 matches. So k is 30 plus a minus 1. And a and b are the distribution over your priors. So any doubt in getting the map estimate? Okay, cool. So in now we are switching gears and doing this full Bayesian inference. In that we are still considering this beta distribution as the prior, and binomial distribution as still the likelihood. So theta hat of family was nothing but over this theta hat of MAP was nothing but and now so as you can see, these both are point estimates, but now we are interested in directly evaluating this quantity. So what we are in all of this we are trying to do this, and the actual formula of this is this. So we are trying to evaluate the entire quantity. So yeah, so let's just do that now. We know P of x given theta is binomial, and P of theta is beta. Just A comma B. These are the parameters. So there is also this parameter n, but I'm just assuming that we have this n, and we are not assuming a prior over that n. So this is nothing but A plus B. And this is NCK theta k1 minus theta n minus k. So for computing P of x, what we would do is, because we have this quantity and we have this quantity, we would just like to marginalize out this. So this is just marginalization. So now we are trying to compute this P of k, the denominator. This would be then P of x given theta. So substitute this here. NCK theta raised to k1 minus theta n minus k. And P of theta, again substitute this here. E plus B, E. These are just constants, and like we know the product of this like directly value is 2. This quantity, right? So I'm just this is what we did earlier for proving the conjugacy, and just taking this quantity and writing it down here. And ck t plus a minus 1.
I think you missed one minus in the top equation of beta.
Sorry?
You missed one minus. You know, where you written a to the power a minus, sorry, theta to the power a minus 1. I think you missed the 1 minus theta b to the power b minus 1.
It's here, no? Yeah, I'm just writing it. So if you mean here, so n minus k plus p minus 1. So yeah,
No,
is there any problem in my
that's fine. Don't
calculations?
worry.
Okay, yeah. So we need to evaluate this. One important thing is that like we can directly do the integration, but yeah, what functional form does this part look similar to? Yeah, anyway.
This look like binomial, isn't it?
So yeah, but so in binomial, the distribution is the random variable is the k. Here we are integrating it over theta. The functional form of binomial and this are same, but if this is a binomial distribution, then the thing that sorry, this is a binomial distribution, and the thing that varies is k. In your so it's a discrete distribution, and the k goes from 0 to n. Your theta is some parameter, the probability of success, that is a parameter of the distribution, and the binomial distribution is defined over the random variable, which here is indicated by k. And and in the prior, the functional form is kind of the same, but now the distribution is defined over this parameter theta, and a and b are the parameters. So that's the difference. And here, since we are we are differentiating it with respect to theta, this is like similar to beta distribution,
Yeah.
which is like what we are saying, that obviously it should be similar to beta distribution, because the product of this, we have chosen our conjugate such that this evaluates to a beta distribution. So now what I would do is so this is one of the tricks that you'd observe in most of this, like evaluating this, what I and here the range is like it's a definite integral over all the possible values of theta, and yep, and theta is from 0 to 1, because the the domain the can you all hear? Can you hear me?
Yeah.
I am not able to hear you.
Hello. Hello.
Hello.
Hello. Is anybody else able to hear me?
Yeah, I can hear you.
We can just, yeah. So now the one common thing that you generally would do here is, because you know the distribution of this thing, that yeah, the functional form, you already know the uh, so you would try to make this quantity uh, same as your distribution, and then you know that within that domain it would directly evaluate to 1. So so what I would do basically here is multiply in the numerator and denominator by k plus a and minus k plus b, and the sum of these, which is nothing but n plus a plus b, and then the integral would become 0 to 1. And okay, I will write it as k plus a minus 1 plus n minus k plus b minus 1, and this would be k plus a, oh no, not minus 1, sorry. So this is what I multiply divided by with, and this is again the same quantity here inside the integral, and then we would have these two terms as usual, theta of k plus a minus 1 times 1 minus theta of n minus k plus b minus 1. And now if you can see is, let's say m is equals to k plus a and n is equals to n minus k plus b, then I hope you can see that then this is nothing but m plus n comma m comma n theta of m minus 1 1 minus theta of n minus 1 d theta. And we know this thing evaluates to 1 because this is what exactly the beta distribution, yeah, the beta, this is nothing but beta distribution over m, and then this thing evaluates to 1. So now what we did is basically this integral, entire integral evaluates to 1. So now what we end up having is this form. So nck a plus b a b a plus k n minus k plus b n plus a plus b. So any doubts still here? Yeah, anyone? Okay, so now this is what p of x is, this entire thing. You would ask like where is x, so okay, so what is a random variable here? Yeah, so can anyone tell me? This thing seems like it's a constant, so is p of x just a constant? Yep. So yeah, it would like it's a fundamental question. So what are we exactly evaluating when I say it's like p of x, and then these are the quantities that I provide?
Isn't that P of X is a normalization constant?
Yeah, over but in a way it is like, okay, it's a normalization constant for theta, because this quantity doesn't depend on theta, and then this distribution is P of theta over X. So as you saw, it's independent of theta and it's a normalizing quantity over theta for theta. But the question is, it's still a probability distribution, right? So yeah, if P of X is a probability distribution, but this thing seems like it's a constant here. Yeah. Anyway, so like, okay, like a simple question. So in in the entire thing that we did, what did the random variable X represented? See, a probability when I say of X given theta. So yeah, what did the random variable X represented? Okay, so I'll just go ahead and say it. So X represents this K wins out of n outcomes, and as I was explaining to you before, that in binomial the thing that varies is this K, the power K. So that's what X represented, right? Binomial distribution K wins out of n outcomes. So if you want to just go ahead and prove, then the thing that your varies is K. So you can do is sum over all the K and just take it, and you'd get one. But yeah, it's like important while doing the math in any of this inference. Math can get quite complicated, but always have this care of switching it back to where you started it from. So even while just evaluating your variables, just remember what each of the variables represents and try to have some intuitive understanding of that. So yeah, when I say like, okay, P of X is just this, you should always remind yourself that it's still a probability distribution. So over what random variable is it defined, and what are the values that the random variable takes. So here you can see that in all of our derivation, X is nowhere because X is the random variable and the value it can take is K. So people would generally miss it, but what I should probably have written is X is equals to K. X is a random variable, but you wouldn't find like everyone explicitly writing down everything over what the probability distribution is defined, what are the values you take, because it would just get tedious and it would look scary. So these are the minor details that gets omitted a lot, but even while taking an expectation over what distribution is the expectation taken and all. So that's what. Yeah, so now we have P of X, now we have P of X given theta, and now we have P of theta as well. So basically we have all the three required quantities here. So let's just evaluate what P of theta given X is. So I'm first writing down P of X given theta binomial, which is nck theta k 1 minus theta of n minus k. This is our first binomial term. This is our beta distribution. And this entire thing would come here. nck. And now you just yeah, many of these things would cancel out. nck and nck gets cancelled out. this entire thing gets cancelled out with this entire thing. And then what we are left is I would take just this in the numerator, n plus a plus b, k plus a, and minus k plus b, theta of adding these into k plus a minus 1, and minus theta, and minus k plus b minus 1. So this is your distribution, the posterior that you wanted. So yeah, so here we got a closed form solution for everything, as we have been saying in the past, that this is always a quantity that you are always interested in, and only very few times you would be lucky enough to evaluate this quantity entirely. Now, any estimate that you want on theta, not just mode, if yeah, if you just want the mode, then you can again, this would be the same as theta of MAP, but you can also calculate now the theta of mean, theta of mean plus some standard deviation alpha times this, and this is my standard deviation. So now you can calculate anything you want, because now you have the entire distribution, the most optimal distribution of theta for you. So let's just calculate the theta of mean, and this mean is also called theta of EAP. Like EAP is expected posteriority. So yeah, as we saw, like theta for getting the MAP estimate, it's quite easy. You just need to differentiate and equate it to 0. But for getting the expected a posteriori, you generally would need the entire distribution. So now, if we want to evaluate theta of EEP, the expected value. So again, now this is the expected value. This would be a point estimate. So it would be just like probability of theta times theta times theta. The thing that this would evaluate to would be this is just a constant, okay, n plus a plus b, k plus a, and minus k plus b. Same, just constant I wrote over here, and then I'm multiplying this value with theta. So what I would end up is getting is theta of k plus a minus 1, theta of theta ratio k plus a minus 1 times theta would just become k plus a, and then this would become 1 minus theta and minus k plus b minus 1 d theta. And yeah, there is an integral over all of this. So like again, similarly, we can just again do this, take this out, n plus a plus b, k plus a, and minus k plus b, and yeah, again multiply with now. So again, as we can again see, this is a form of beta distribution, belongs to the same family. So just multiplying out with k plus a plus 1. So why I multiplied is k with k plus a plus 1 here, I am trying to do is theta of raised to m, 1 minus theta m minus 1 and n minus 1. So for me to do that, I need my m to be k plus a plus 1 and my n to be n minus k plus b. And then again, summing both of these, we would get n plus a plus b plus 1. And within the integral, we would have the exact beta distribution over k plus a plus 1 and then minus k plus b. And we know the distribution is over theta, and we know this quantity value is 1. So yeah, again same thing as we did before. then this now we would use this identity that I told you about gamma function earlier and try to cancel out this term. So k plus a plus 1 would be k plus a times and then this k plus a and this k. Okay, I'll just write it out again. So I evaluated this to this k plus a plus 1 to this quantity, and this will also stay this. And k plus a minus k plus b. Again, this can be evaluated to n plus a plus b times n plus a plus b. So now we can see this and this cancels out, this and this cancels out, this and this cancels out. Okay, sorry, this doesn't cancel out, this and this cancels out. So now we are left up with k plus a times n plus a plus b. And yeah, this is your expected a posteriori. So yeah, for everything we got, this is okay. I'll just type theta hat of MLE was just k by n. We didn't have any a and b because we didn't assume any prior. Theta hat of MAP that we obtained was k plus a minus 1 and plus a plus b minus 2. And now the expected a posteriori was just k plus a and plus a plus b. Okay, so any doubts still yet? So I think by now you should be like pretty familiar with all of these MLE, MAP, Bayesian, inference, all the three quantities, and like get inside your head. So what are we evaluating? What we are getting is a point estimate or not? Are we considering any priors or not? Are those priors conjugate or not? Are we making that explicit assumption? So yep. So anything till here. Like these concepts come up very frequently, and I hope you are now comfortable with all of these three quantities.
Can you scroll up a bit? I had some up. Yeah, here a bit down, I think. The theta hat EAP. That p theta, is that p theta or that is the posterior? Because I think you.
It's
okay.
Anything else? Any other doubt?
So can you scroll up? So when we get the final posterior expression, so in order to interpret it, theta is the probability of success, right?
Yep.
And so this is a beta distribution kind. This follows a beta distribution, right?
Yep. Like we
where
chose a
k
prior.
Varies,
yeah.
Where k varies from so.
No, so this distribution, if you need to prove that okay, this is the distribution, then you need to integrate it over theta. Like theta is the random variable here because the k comes from this x. X basically says k wins out of n.
Okay.
And this is given to you. And so k is not variable here because you are defining your distribution over this theta.
Right.
Yeah. Any other doubts?
I've got a similar question here at theta EAP.
Okay.
So you got the that's the likelihood. So don't we need the prior there? Because I didn't get it. You just multiplied this by theta. Is that right?
Yep. So okay. The way like what we did here is now once we have this posterior, so this is the entire distribution that we were always interested in. So now we have seen all our data X. The prior is like some okay. So like from where we started is this, and this is through P of X. We can. So now this theta is basically saying, okay, I don't know anything about my data. I don't have any clue. Just based on the previous information and just the knowledge of my world, what is P of theta, the prior. This is okay. Now I have seen my data. Then what's the likelihood of if I define my theta to be some particular value, for that theta, what's the likelihood of seeing the data that I was given? So basically that we calculated the likelihood in P of X given theta. And this quantity that we obtained was the entire distribution of the weights that we were talking about earlier. Yeah, entire basically the distribution of weights given your eh, so basically like P of theta would look like something like that. MAP and MLE would just give you this quantity, but now the thing that we obtained was this entire distribution. And since now we have this entire distribution of theta, now the cons of those approach were exactly that we only got this quantity and we weren't able to evaluate or theta on any other quantities. But now you can do that, right? Because now you have this entire distribution. Now what we are just doing is the expected value of this distribution rather than just focusing on the mode of this distribution. So let's say the expected value is something here. Then yeah, so since that's what exactly expected a posterior means, expected value of your posterior distribution. And yeah, so the expected value of theta would be just like the distribution from which theta comes from. And now so that's why I wrote initially theta, that but the distribution from which theta comes from is basically this your posterior distribution. So it's theta given X times theta times d theta, just the definition of expected value first moment.
Right, got it. Yeah.
Was that clear? Yeah. So yeah, any, so now I guess it's just two of you, right? Yeah, okay, cool. So that's all I wanted to say about MLE and MEP. And then this A and B kind of comes from your prior distribution. Like if you have, let's say, if you have some knowledge that in the previous tournament, for we were calculating it for particular example, if the data was K wins out of n matches, and our data was exactly 30 wins out of 38 matches. So K would be 30, N would be 38. And now the beta distribution that we would define over here would be dependent on the prior data. So let's say our prior data was, okay, I'll keep it just low. So before the tournament, let's say Arsenal played some practice matches, and the thing that we saw is it 2 wins and 2 losses. So this is the prior data that we had, and then so for this you can have the distribution that you can define it over is beta of 2 comma 2, where A is 2 and again B is 2. So if you define based on your prior knowledge something like this, then it makes sense to incorporate this and this to your so basically the total number of wins would be K plus 2, and out of A plus B prior matches, so N plus 4. Again, K is 30 and N is 38. So that's how you would compute kind of in the real world. And but okay, and to get back to your previous doubt, Deb, so one way we did this was try to evaluate this integral by now since we knew the probability distribution, we kind of cheated it a bit, that okay, we know this is a probability distribution, and then we tried to multiply it with those constants that would directly evaluate this distribution. But the other thing that you can do is, now once you have this map estimate, yeah, so now, now you know that okay, it's going to come from beta distribution, and now you have these parameters, and you know the output is always going to be distribution. And since you know this, it's beta distribution, you can directly get your constant from these two parameters. Like if I say you it's coming from beta a comma b, then you directly know the constant is this. So and that's what we sometimes do in normal distribution. We don't calculate the mean and standard deviation explicitly, but now we have this polynomial term, then we can just directly compare it with as I was saying in my previous lecture, we can directly compare it this form, and then directly obtain the nu and sigma, rather than always rather than calculating nu and sigma. If you know the output distribution is going to be normal over this nu comma sigma, then you can just directly do this. So did you understand what I was saying? So you always don't need to evaluate your integral if you already know the distribution. Then since because this quantity this quantity is independent of theta, right? And your output is a distribution over theta. So that's why we call it a normalizing constant, because all it does is just ensure that this integral, the entire integral evaluates to 1. So if I provide you, so when I just multiply these two distributions, obviously you need to ensure that the new distribution that you get is a proper PDF, which when integrated evaluates to 1, and that's all p of x basically does here is make sure that whatever data that the output that you get, it normalizes it and ensures that the distribution is 1. And since it's independent of theta, we call it a constant. So that's what in the lecture they were referring to, that and it's kind of both the same things, just instead of year just multiplying and dividing it, what you are essentially doing is kind of this is evaluating to your posterior. This is exactly what we ended up with in MEP, and so it's a conjugate distribution because it belongs to the same family. And when we are multiplying it, dividing, we are just what we are dividing it with the normalizing constant itself. So so the other way to do this would be, now you have multiplying this and this, it belongs to this family. Like if I just multiply this and this, it belongs to beta distribution family, because that's how you chose your prior. And k plus a minus 1 and n minus k plus b minus 1 are my parameters. So instead of calculating all of this, I know the constant would be just this m plus 1 and m and n plus 1. M and n plus 1. So you can just directly obtain this. Where did it go? Yep. This thing, and then this is just that constant that you need to divide it by to keep it constant, to keep the integration within that. Does it answer your doubt?
Yes, it does. I mean, so what we did in map, we multiplied the likelihood with prior, right? And they were, and we choose the prior as a conjugate prior, so we know the distribution of the posterior.
Yep.
Right. And when we're doing the full Bayesian inference here, when we did the integration of this for p of x, we did the integration, and this is nothing but the likelihood times the prior. So we know the distribution of p of x in this case as well, which is exactly same as the posterior. Right.
Yep. Yeah. So not the so the distribution. Like it's correct, but it's like you would call it a normalizing constant only when you call it with in respect to because you are doing all your evaluation on theta, and p of x is independent of theta, you would call it a normalizing constant in that sense. But still, p of x is yeah, it's still a distribution, it's some distribution over x, but we are not interested in this distribution because the distribution it is over is something that's already given to us. So it's a distribution over x, but we already know x, so that's why it becomes kind of a constant.
Right, okay. And what if we don't know the distribution?
So we don't know the distribution as in?
Like if we don't know the distribution of p of x, like this time we know because we know it's a conjugate prior, right?
Yeah.
But what if we didn't know that?
Yeah, so as I said, we did that because we wanted to know p of x. So even in the lecture, as I said, choosing conjugate prior ensures that you know the distribution of p of x. But so one of the reasons to choose conjugate prior is also that you don't want your posterior distribution to change, right? So if I knew that p of theta was yeah, so if I knew p of theta followed some distribution, then after seeing some data x, I would want to update that distribution, but I wouldn't want to like change the distribution entirely. So yeah, in our case, we observed that p of theta was some beta distribution, and then we saw some new variables, new data x come in. So if in this case, yeah, so we knew like 2 wins and 2 losses, and then we saw okay, now we also know this it has 30 wins and 38 losses. Then we still wanted to be like okay, now we have more data, we still want to update the parameters rather than just completely change the distribution by itself. So that is one reason to choose conjugate prior, and the other reason is just to make the math easy, and now you know the but yeah, if you didn't know the distribution, then you would have to integrate it entirely, because then there would be no the normalizing constant, you would need to still evaluate it in order to make it a proper probability distribution. And then in that case, you would need to multiply both of these, you would get a new distribution, some like weird functional distribution that wouldn't have some name for it. We do in this case, like it's a beta, but just multiplying two random variable two distributions and normalizing it would give you some completely new distribution with and then you would still need, in that case you would need to integrate it to normalize it. So like in that's where a kind of a divide comes in, where in all of general statistics, Bayesian inference, you only deal with the distributions that we know of, and like if I just give you some random distribution, say f of x, uh, which for which you don't have any information, then even to evaluate the expected value of f of x, you would need to integrate it with respect to x, assuming f of x is continuous. But sometimes if you know already the function form, then you can just equate it to so if I just told you f of x was a normal distribution and just give you the functional form, you can just compare it with x minus mu the whole square and just get the mean out directly out of it. So I think if you want, we can take a break, or then if not, we'll just proceed to latent variable models next. But that's this was like the first part where I wanted to, but yeah, I hope that you are comfortable with MLE, MAP, EAP, full Bayesian inference, and you don't have any doubts regarding those aspects. Okay, do you want to take a break? Do you want to revisit something, or should I just go ahead without any segue and directly jump into latent variable models? Kushal, Deb.
I think we can continue.
Yeah, we can continue.
Okay, nice. Yep. So let me just let me ask you this question. So okay, um, so this is like kind of a motivating example for latent. So what latent variable model simply like a high overview would be kind of, you have this X features, you create your own new latent and you want to do the prediction for Y, but instead of directly doing this prediction, this is like very high level overview. You take this X, find this new latent variable Z, and then you do the inference on Y. So why this has some advantages. So this Z is completely introduced by you. No one provided to you. Yeah. So just to make math simpler, just to make things more sense, you would introduce this latent variable, which would be dependent upon all of your Z, X. It's okay, X1, X2, X3. These are my initial features. Then I would first get Z1. Let's say I would also get this Z2. And then I would do this prediction on Y. Rather than directly going from X to Y, we go from X to Z, and then we go from Z to Y. So, okay, let's say if so a motivating example for this would be something like, let's say Feinstein wanted to take some IQ test. Yeah, let's say he gave the GRE math exam. So if Einstein gave the mathematics exam of GRE, how much would you think he would score, and on what factors did you make that decision? Yeah, so let's keep it interactive. Now it's just the three of us. So yeah.
I think he would do very well because it's basic arithmetic, and I think if he can think about relativity, he should be good with arithmetic, geometry, and all those simple stuff.
Yeah. So how did we make this decision? So for us, like let's say I give you the entire everything Einstein ever did. So we so like all the features that's available to us, like his grades from first standard to till college, till whatever degree he achieved, all of its grade, all of its publications, and we didn't sit and relate to each of this. Okay, if the grade in if the grade in third standard, how does that correspond to how does that correspond to your GRE score? How does this correspond to GRE score? In like mentally, what we basically do is, okay, he has all of these impressive things. He must be intelligent. He must be smart. And then since he's intelligent and he's smart, he would score well. That's how even in our minds while doing inference, we break it down in that way. And now Einstein's intelligence and Einstein's smartness is not some quantitative score that's given to us, but then how did we determine that he was smart? And we determined he was smart based on all the knowledge of Einstein that we had. He published so much papers. He got good grades. He came up with things that nobody else came up with, and like using all of these things, we first inferred that okay, he's smart, and then because he's smart, he would he would get good grades in GRE or in any of those IQ tests. So this so even in our mentally, we made this latent variable model of smartness, and that's like similar to even in a real life example. So if someone get good grades, if someone plays good at chess, or like all the things that would go into smartness, you first like define okay, you first get okay, that person is smart, and then once you have that person is smart, and then you would infer based on the future outcomes. You wouldn't correlate every feature with every other feature, like okay, his GRE score would, how much is it dependent on his score of his CGPA in the first year, his CGPA in the second year. So that's basically an intuition for latent variable models, and how it's applicable even to us. So it would make sense to model our assumptions based on this latent variable models. So first of all, I hope it's clear to you why does it make sense using latent variable models. And let's say if we didn't use those models, and if we have x1, x2, x3 and x4 features and we needed to predict y. So okay.
So you are saying that our assumption that Albert Einstein is smart is a latent variable model in our head.
Yep. So the smartness of Einstein is a latent variable. Yeah.
Okay.
And
from that we are inferring that he can do anything, GRE or all those exams.
Yep. So because no one quantified Albert Einstein's smartness to you, and like that data wasn't ever provided to you, you inferred it initially based on all everything Einstein did. So so that is from X to Z, you inferred that okay, Einstein is smart, and since he's smart, you score good. So if we didn't use latent variable models, let's say this X1, X2, X3 and X4 other features, let's say this some okay, these are the number of papers that he did. This is let's say his grades in school, and this X3 is the number of innovating things that he came up with that no one else did, and like all of this. And now if you need to predict his let's keep it with GRE math score, then first so these are the assumptions and you would make is okay. Yeah. So can anyone tell me if I make these assumptions that y is dependent on x1, x2, x3 and x4, but x1, x2, x3, x4 are independent of each other, then which kind of model would this be? Directly predict y from my features, but assuming that all of these features are independent of each other. Okay.
This is classification. No.
The classification is like generic, but this sort of like the main assumption here that we are making is that all of these are independent of each other. Okay, and these are not the data points. Again, so I always for me it always becomes clear. This is a strong assumption that your features are independent of each other, and like saying your data points. The data is IID is generally lax assumption because it's what we normally see in most of the cases. But saying that the features are independent of each other is always a like very strong assumption. And okay, so this is a just naive based model.
Okay.
So where you just ignore I think we covered. So if it's probability of y given x1, x2, x3, x4, you would just calculate it like this. And we know this is rarely true. This doesn't happen often, and this doesn't provide good results. Like let's say if we are in the same example, we are measuring some person's intelligence, and okay, let's make it more explicit. X1 indicates his grades in school, grades in college / university, some IQ test, and this one would be let's say some mathematical aptitude or chess score or anything that you would think would define person's intelligence. So we know all of these are kind of correlated to each other, right? You can't necessarily always say that even we know that even while doing this latent variable inference, we know we kind of are assuming all of these give us x, and this would make all of them like dependent on there is some correlation between them. That correlation, like you can call it like itself the intelligence, like because if person's grades in school are very high, then the grades in college and university, you'd probably expect them to be high. So yeah, so in order to do this proper inference, what you would actually need to do is assume that all of these are dependent on each other. So yeah, you'd kind of get a fully connected graph, and then you would have to do inference on that aspect. So doing that would be, it's pretty hard. So in that case, you just you won't be able to factorize it like this, but you can factorize it like using the chain rule of probability. So this would evaluate to okay, let's say you are interested in getting the joint probability of all of this, then it would evaluate to x4 times x3 x4 x2 given x3 x4 times x1 given x2 x2 to x4 and y given this. So this is just chain rule of probability that we went over in the first lecture. And then basically you would need to model each of these probabilities, multiply it, because it would be a fully connected graph, and that's get pretty complicated in that aspect. So introducing a latent variable model would also simplify the math for us highly. So in that case, would have something like that. Yeah, so now we would infer first this z, and then we would infer this y. And so while doing so the way then we would do it is kind of do this full Bayesian inference on y. So yeah, we'll see an example of that. But then now you can just make this assumption that first p of y is only dependent on z now, and then you just need to model this probability. Then you need to move to this phase. So it's kind of two-phase problem. First, get your distribution on latent variable, and this latent variable sometimes is yeah, sometimes you wouldn't even understand this latent variable distribution. You would just model it, and then from this latent variable distribution you try to estimate, yeah, the probability of your outcome. So like some examples of this latent variable models are, so k means is one of the latent variable models. So yeah, we would look at this PCA. Yeah, people sometimes also call it probabilistic PCA. Then GMM, probabilistic clustering. So these are some of the examples of like latent variable models here. And yeah, when you and all of these is this different assumption how does z come in, yeah, so x to z to y. This is a normal nomenclature that GMM just means Gaussian mixture model, by the way. Yeah, and what we would I would always be the outcome that we are interested in. The x is the given data slash features, and z is a latent variable, not provided, no clue. So yeah, whenever I write x, z, and y, just remember this thing.
So outcome, what is the outcome? On what type of
outcome, basically, in the sense, the thing that you're trying to predict.
Okay.
So okay, let's say in k-means, it would be simply like a 0, 1 value that would say, okay, this belongs to this cluster or not. And in PC, in GMM, it would be, in GMM, it would be the probability that it belongs to every cluster. So if you're not familiar with probabilistic clustering, it's same as clustering, but instead of providing hard values, we provide kind of soft values. So if let's say we are C1, C2, C3 are 3 possible clusters, then a k-means would say something like this, whereas this is called hard clustering. Soft clustering would be 0.2, 0.6. Yeah, this is something GMM does. This is something k-means. So depending on the problem, your prediction would change. And our latent variable would be something like that tells us, okay, it belongs to like when we'll go through that example here, the distribution on latent variable basically kind of provides you with this probability that it's a categorical distribution over each cluster, so a probability of which each cluster probability of that data point belonging to each cluster. So I would I think I would introduce Gaussian mixture models here. So I think you're familiar with k-means. If given the time, we would go over the probabilistic PC in detail. The book, even I forgot the author's name. But I'll provide the reference, but even that has a good amount of literature on probabilistic PC, and we'll do that once we complete with EM. But I hope you both are familiar with k-means.
Yeah.
So we will do an example of k-means later. I would just now introduce GMM, and then maybe we'll stop for today. GMM, and then we'll also do GMM after doing EM algorithm once. So I think next week we'll go into the proof of EM algorithm. So what GMM basically, as I said, first you need to fixate on how many clusters you need to do the inference for. C number of clusters. This is kind of a hyperparameter you just choose. You are not trying to infer the C. This is something that's already provided to you. Now, for me, sometimes it personally it makes like intuitively it makes sense when you kind of assign a story to it, like how the data actually came out to be the data that X that you were provided, and that's a very good way to have an intuition of how this what does the latent variable signify. So story for GMM would be something like the data that was provided to you came from some process, some generating process. We don't know that process. We are like, we are trying to guess what that process exactly is. But for making sense of my method, I'm like kind of backtracking. And let's say if we knew that process, then Gaussian mixture model basically what it does is, okay. These are my data points. I'm assuming there are 3 clusters here. So let's say if Gaussian mixture model, it's a mixture of Gaussians basically, where we are trying to let's say we choose a C to be 3, then we're just saying that okay, the data comes from 3 different sets of Gaussians. Then in this case, what we would generally estimate is, okay, this is our first Gaussian, this is the second Gaussian, and this is our third Gaussian. I ideally would like to come up with this, and then this data point kind of equally belongs to all of these Gaussians. So for every data point, we would have this vector of that belongs to R3, which basically says probability of it belonging to first cluster. It's a cluster A, cluster B, and cluster C. So you want this vector basically, probability of second cluster and third cluster. This is some data point X, probability of X belonging to these clusters. So let's say just pi1, pi2, and pi3. So we need so this is basically simply a discrete distribution over 3 different classes. And obviously we would need pi1 plus pi2 plus pi3 is equals to 1. We need to obtain this, and so there are in a general case there would be C quantities of this. And so what we would do is sample from this distribution first. Let's say, okay, there are just 2 Gaussians each, and let's say we are trying to guess from where this data point comes from. You toss a coin, and let's say pi1 and pi, just for 2 Gaussians, pi1 and pi2 both are 0.5. So toss a coin from and pi1, and so what I mean by this is toss a coin. If it's head, then sample from n1 is some normal distribution. Gaussian distribution. So if you want to sample data from this underlying distribution, what you would generally do is toss a coin. If it's head, unbiased coin, because we are assuming pi1 and pi2 both to be 0.5. Toss a coin. If it's head, then sample from first normal, and if it's tails, then sample from this second. And that's the kind of that's the kind of data we would observe this to be. In this case, now it's a instead of tossing a coin, maybe you have some just sample from a categorical distribution. We would, if we have the time, we would go more deeper into sampling later. But sample from a categorical distribution, and based on the sample that you saw, just the normal that corresponds to that cluster, just sample from that normal distribution. That's what you would observe. So now in this case, what you are basically simply doing to generate your data is you are always sampling from this normal distribution in order to create data. But from which normal you need to sample to, you are choosing this latent variable, which simply gives you the probability sample from of it belonging to ni of it belonging to I. Sorry. So the thing that you are always interacting with is normal distribution. You are the final data point that you would observe is always going to be from one that you observe. So so if it's this data point, let's say the data point that you observed, what's the probability that is sampled from this A? Obviously it would be non-zero, but very, very low probability. Again, what would be the probability that it was sampled from B? That's the latent variable here. And what's the probability that it was sampled from C? So I hope you understand what the latent variable is. So here the distribution of latent variable is categorical distribution. And this is what you made, and you made this assumption, right? Like, provided the data, no one told to you that, okay, there is this latent distribution of categorical variable of categorical variables that you need to estimate. It's an implicit assumption that you made because that's the problem that you are trying to solve here. So distribution of latent variable is a categorical distribution. And now, yeah, so let's say you have this particular data point xi, and you want to measure what's the probability of yeah, given your parameters, what the probability of seeing that data point is. So Gaussian mixture model tells us is basically do this. Again, let's say we just have 3 classes. Yeah. And theta is simply all of these. So it would be pi 1, pi 2, pi 3, nu 1, nu 2, nu 3, and sigma 1, sigma 1. Cool. Yeah. So you need to estimate all of these parameters. Oh, okay. So yeah, and you need to optimize for this thing. So now a question. So, let's say if x belongs to Rn, n-dimensional Rv, then what are the total number of parameters that you need to estimate? Yep, anyone? Just give it a shot. Are you working on it? Do you have no clue? Hello.
Would it be n square? Hello.
So you need to just simply calculate what pi 1 is, what nu 1 is, and what sigma 1 is. So yeah, if I was not clear before, it's like this nu 1 and sigma 1 are the parameters of this normal distribution, and pi 1 indicates what's the probability that it was sampled from this first normal, what's the probability that it was second normal. If this is a probability that it was sampled from second normal, then what's the probability of me seeing that data point given that it was sampled from second normal? And so yeah, the probability of it being sampled from third normal, and this is if it was sampled from third normal, what's the probability? Yeah, so for this case we would have yeah, for this point we would have pi 1 very low, very small, even pi 2 would be very small, and pi 3 would be huge, and this normal n3 value of x given nu 3 comma sigma 3 would also be huge. But let's say if this is the point that we are trying to look into, then again pi 1 pi 2 would be very high, pi 3 would also be very high, but n3 value would be low. You can see, right? Because if it's this normal, then the mean would lie somewhere around here. So the probability of this point being sampled from this would be very high, because yeah, for a and b it's just too far off the mean. But yeah, for this seeing this point, even though the probability of it being from this distribution is high, the probability of it being sampled from that normal is low because it's quite very far from the mean. So yeah, so this and this new one, yeah, these are just the mean of these 3 normals, and these are the variance of those normals. And yeah, so if I just told you all of this, like what are, so we are interested in obtaining this theta, so that's what we are going to work for. But let's say if I just provided you the theta entirely, so just told you that okay, this is how all the points are sampled. Then I provide, then while doing the inference, what I would simply do is, okay, I saw this data point xi, and then I would just calculate all of these three things and then just add it up. Yeah, so back to the original question. Yeah, value of how many parameters are you trying to estimate here?
So in this case, we have got total 9 parameter, right? Because it's all this.
Yeah, but some of these is, so yeah, it would be 9 parameters if x belong to just a real number. But now x is an n-dimensional random vector, so not all of these are scalars. So
right, okay, based on this one, so what do you mean by like, is it going to be like 2 to the power n plus 1?
No. Okay, so I'll just answer. So pi 1, pi 2, pi 3 are always a scalar. It's just a categorical distribution that says, okay, probability of pi 1, first cluster, second cluster, and third cluster. But now nu I would be a vector, right? If you remember that for for multivariate Gaussian, nu I is if n belongs to, then nu I would also belong to this n-dimensional vector, which would be just expectation of x1 till expectation of xn. And sigma of n cross n would be, sigma would be a covariance matrix of n cross n. So the total number of parameters that you would need to estimate is 3 plus 3n plus 3n square. So 3 plus 1 plus n plus n square. Does that make sense?
So is that the expectation of x1 till expectation of xn are considered as multiple parameter, or you taking this whole as one parameter?
Yeah, no, multiple parameters. These are n parameters, right? These are n parameters, and then we have three such means news, and so that's where 3n came in. And for sigma, so these are scalars, these are vectors, and these are matrices. So 3, or ideally instead of 3, to keep it more general, it would be C, where C is the number of clusters. So I these are n just different parameters. So what is clear? Yes, so, sorry, go ahead.
Okay, yeah, it makes sense. For the mu, that makes sense. But for the covariance matrix, if we like using a spherical covariance matrix, then we're going to have only one parameter, right? Because then it would be multiplied by the identity.
Yep. Yeah, definitely. I'm just considering the general scenario where it might be entirely different. I'm not making any assumptions that we are only having diagonal entries or all the diagonal entries are same. But yeah, you are definitely right. If we make this assumption that it's sigma square I, simply all of these are the same values, then we would instead have just n square would just simply become 1. But without any assumptions, let's say for now, there are no assumptions and we are simply trying to do this. So so now let's simply do this maximum likelihood estimate, because in this case, for doing GMM, we don't generally have any knowledge about our priors of what new eyes can be. Because we don't mind, right? Like if the mean of this, it's just a probabilistic clustering, and the mean of that cluster can lie anywhere in the real space. So let's just show a maximum likelihood estimate. If we say we were given okay, let n is the number of dimension of each single data point. Let's say we were given m data points. So m is basically simply the size of the data set, and I is equals to 12 probability of x given theta. So this is the quantity that we are trying to estimate here. And so and all of these xi's are given to us, so we can just simply plug in okay, this would be let's say summation over all the clusters, j is equals to 1 to c pi j xi nu j. So I haven't explained this, but does it make sense? Should I explain it or should I just move right ahead? Like it just comes from this thing here. Yep. Yep. Okay. So now we can, yeah. So we want to maximize over this theta, and when I say theta, theta is all of these 9 things. So let's say, can we do a simple gradient descent over here? Just yeah, if we simply do now we have this quantity, we want to maximize over this, just start with some random values and keep moving towards the direction of the highest gradient. We would end up with some value, a local optimum, and say, okay, this is my yeah, these are my values. So yeah, so what's the wrong thing that I'm doing here? If I simply put this entire quantity in gradient descent algorithm, who would just give me some maximum.
I mean, isn't that the gradient descent can say that the sigma value can be all 0, and we don't want that, because I mean we need to make sure the sigma is always positive, semi-definite.
Perfect. Nice. So yeah, it can not just 0. It can give you any random value, not random values, but it might give you values for which you wouldn't obtain a covariance matrix corresponding to that, because you want your sigma matrix to be yeah. So okay. So what are the different constraints? So there are 4 constraints here that you need to ensure. So one of them is sigma is PST, positive semi-definite. Yeah. What other constraints do you think that you need to ensure here while doing this optimization?
And the sigma should be symmetric as well.
Yep, perfect. Other ones. Yeah, one of the constraints I think I had mentioned previously. You could observe it here somewhere. Yep. Yeah, this is the constraint basically. So you need that this is a categorical distribution. You need to ensure that summation of all j's, this one, and at the same time, since it's a categorical distribution, for every j, no, sorry, for all the j's, you need that this. So these are the 4 constraints that you need to keep in mind while doing optimization over gradient descent. And you can then one way you would do this is simply like do sigma square I, and then you are basically you are getting rid of all of these constraints, and third and fourth constraint, because sigma square I is always symmetric and sigma square I is always positive semi-definite. Yeah, sigma can belong to any real number, and then yeah, then these are the only 2 constraints that you might be left with. You would also reduce your number of variables, but then you are basically restricting your hypothesis space to only such distributions as sigma square I. Yeah, this to a simply spherical distribution, spherical normal, if I would say. And then yeah, so you can do that, and then you can plug it into gradient descent. And for ensuring this, you can simply do Lagrange optimization, where you can add in this. So yeah, are you guys familiar with Lagrange optimization?
I don't remember, to be honest, top of my head.
Yeah, okay. So
is it Lagrange optimization or multipliers?
The lambda are called Lagrange multipliers, right?
Right. Okay, that's what you mean. Okay, got it.
Yeah, so so you can just simply plug in this extra constraint. So right now it's not necessary. If we get the time to do probabilistic PCA, then I would give some time to this. But yeah, so you can also ensure these two constraints are met, and then just do a simple a gradient descent search. But you can also solve this using EM algorithm, and which I think we would go for it in the next lecture. Go over the generic EM algorithm for GMM, and so intuitively how you would go about doing this, it's a like multiple step process, similar to k-means, if you are familiar to that. So initially you so let's say, should I go into that? Okay, so for new I,
so just to remind you, we're almost at 2.5 hours.
Yeah, okay, so I think it's better to just keep it for tomorrow. So yeah, this was not tomorrow, I mean the next review session. So yeah, this is simply basically what GMM is. I hope you have familiarized yourself with Gaussian mixture models, and in the next lecture we would go over EM, and then we would revisit GMM from the perspective of EM algorithm. And I haven't mentioned this, the formula for just doing simply the getting these new sigmas and pi i's, and it makes a lot of sense intuitively, and we would derive the formal proof using EM algorithm for the next time. And I would suggest like just see what Gaussian mixture model algorithm does, and it makes a lot of sense intuitively, and so, you might not even require formal proof for it. You would just say, okay, this makes much sense. But yeah, EM algorithm would give a formal proof of why that makes sense. Yeah, so any questions? Like from my point, I think I'm done for the day. But yeah, just try to work some examples of conjugate pairs, and also see like it's not necessary to get understand EM algorithm to understand GMM. You can directly understand GMM. So yeah, try to see what the Gaussian mixture model does, and how it calculates this pi and sigmas and means and all of that. I think even in DJ Sangvi, like in machine learning course, we had Gaussian mixture models. Okay.
I don't remember that.
Yeah, like they introduced it calling expectation maximization, but they didn't teach EM at all. They just taught like expectation step and maximization step of GMM.
Oh yeah. Now I remember. EM I remember because we used to see videos just a day before exam, so I remember that. But
yeah,
it was highly unintuitive.
And also it was like not the like